Good morning. My name is Keith Hare from JCC Consulting, and I would like to spend a few minutes this morning talking about the status and current directions in standardization for various parts of the big data puzzle. The topics I'm going to cover are a bit about the JTC1 Study Group on big data. I'd like to spend a few minutes talking about what big data is, what the driving forces are, how big really is, and discuss a working definition of big data. I want to take a look at where standards can help big data and what the JTC1 Study Group on big data recommended. And we'll talk about the standards path forward, and finally spend a few minutes on why you should care about big data standards. But first, who am I? I've been a senior consultant with JCC Consulting for 30 years now. We specialize in high-performance database systems and in replicating data between database systems. I also have been participating in the SQL Standards committees for quite a while now, and I've ended up as the vice chair of ANSI INCITS DM32.2, which is the US SQL Standards Committee, and as convener or chair of the International SQL Standards Committee, JTC1 WC32 WG3. And most recently, I served as the chair of the US Big Data Ad Hoc, which was the US technical advisory group to the JTC1 Study Group on big data. Okay, big data standardization. The JTC1 established a study group on big data at its November 2013 plenary. The study group on big data held 4 face-to-face meetings in 2014 and 2 electronic meetings, and completed a report for including recommendations to JTC1 about where standards efforts should be placed in the big data arena. The report integrates ideas from multiple standards development groups and organizations and national bodies, and was delivered and reviewed by the ISO IEC JTC1 plenary in November of 2014. Okay, as a sidetrack, before we go too much farther, I've been rattling off strings of letters and numbers such as ISO IEC JTC1 WC32 WG3. So let me take a look at what all of those gobbledygook actually means. ISO is the International Organization for Standardization, one of the premier standards organizations in the world. IEC is the International Electrotechnical Commission. JTC1 is a joint technical committee underneath both ISO and IEC, so ISO IEC JTC1. SC32 is Subcommittee 32, which is responsible for data management and interchange standards. Underneath SC32, there are currently 4 working groups: e-business, metadata, database languages, where I work, that does SQL standards, and then SQL multimedia and application packages, WG4. Okay, what is big data? Well, big data has hit the trade press and the news a lot in the last couple of years. And it's often described using 3 V's or 4 V's or 5 V's, or I've even seen a 6 V definition of big data. And the V's are referred to characteristics such as volume, variety, velocity, variability, and veracity. It really is an imprecise definition because the problem space is imprecise. What's going on is that we're seeing a paradigm shift in data storage, data retrieval, data analysis. And I want to talk about that paradigm shift and the driving forces, spend a moment on how big really is, and then come back to a working definition of big data. The paradigm shift has several factors, several characteristics. database users are attempting to handle larger and larger volumes of data, and in doing so are pushing past the current restrictions of SQL databases and database vendors. They're looking at highly distributed databases, highly replicated databases, and you distribute databases to handle the volume, you replicate it to handle the potential issues when it's distributed to make it highly available. So they're looking at large data volumes. In all of this, organizations, groups are reluctant to spend a lot of upfront time planning and designing. They want results quickly, and so a lot of the big data type products are designed to accept whatever data is put in it and sort of figure it out later. Another characteristic is that when you start installing software on 100 machines or 1,000 machines, licensing costs add up very quickly. So for a lot of the big data projects, they are using open source database products with minimal upfront licensing costs. The disadvantage is that you also get minimal upfront documentation and minimal upfront support. But if that trade-off works for your application, then the open source products work very well. The driving forces really are that storage, data volume, the storage of data, the amount of data we can store has gotten very large and very cheap. And compute power has gotten relatively inexpensive to what it was 10 years ago or 20 years ago. So we can store a lot of data relatively cheaply. We can use a lot of computers to store that data and to analyze that data. And the next question is, what can we learn from that data? So there's a term that's been used, next generation analytics, and the idea is that instead of analyzing the data to see what happened last month or last year, we're moving towards being able to do analysis that is in line as the data appears, and move from explaining what happened to predicting what is going to happen. So this type of analytics can operate either on data at rest, data that's stored someplace, or on data as it's coming through, streaming data. The other characteristic is that projects and people are looking at analyzing multiple types of data sources, multiple types of data, and that adds some additional complications to this picture. But the end goal is really looking at the data that's available and trying to figure out what questions can be asked and what answers can be gotten from that data. The idea is to be able to use the data to find something that, some information, something that can make an organization or a company more efficient, or allow it to earn a bit more money. As we get into more and more complex data storage and data analysis, there's a personnel issue. The problem space is too big or complicated for a single person or a single set of skills. So we need some combination of a domain expert who understands the problem space, understands what the data is and what types of questions it makes sense to ask. We need a systems expert who understands the technology for storing and retrieving the data. And we need somebody, a data scientist, who understands something about the problem domain, but also understands the algorithms, the statistics, the programming, etc. And my claim is that standards will make it easier for all of these types of people, types of skills to work together and to get benefit from the data. So how big is big? Well, we're used to now talking about data in terms of terabytes or petabytes, and the terms exabytes, zettabytes, and yottabytes have been tossed out and discussed. But as we do this effort, I don't want to be limited by simple yottabytes. So I've taken a look, and the terms that seem to be used for the next order of magnitudes beyond yottabytes are brontobytes and gigabytes. Now, these terms have not yet been officially recognized by the International System of Units, so they're still subject to change. When you start distributing data, putting data on a single server is something that we understand well. Putting data distributed across a cluster of servers has been done for 30 plus years at this point. Distributing multiple clusters in a data center, we know how to do. It gets a little more complicated when we start distributing data centers across a continent and distributing data centers across multiple continents on a planet. But if we're going to do this work, we want to make sure that we don't limit ourselves just to a single planet, and we need to think in terms of what happens if we start distributing data across the solar system, for example. A offsite data center on the moon might be a reasonable answer in some types of situations. Okay, so back to a working definition of big data. We still haven't come up with anything that works better than talking about the V's of things like volume, variety, velocity, variability, availability. Well, availability really doesn't start with a V, but it does have a V in it, and it is a critical characteristic. These are imprecise terms, but I think they're useful for understanding the problem space. And the problem with any time I've seen definitions that tried to be more precise than these terms, the definition ended up limiting the problem space, and it wasn't thinking big enough. And this is all really relative, because what was impossible yesterday is big data today, and tomorrow it's going to be trivial. So we need to think in terms of standards and technology that's not really limited by our current understanding of what big really is. But one of the characteristics is that the requirements can't be met on a single computer. And so we have to distribute the data storage to support the volume and velocity, and once you distribute, you replicate to provide availability. Moving this volume of data across a network is not really possible because of the data volumes and the network delays. So what we need to be able to do is move the questions, move the analysis across the network to the various nodes in the distributed database and move the answers back. So we're moving only a small amount of information, not a large amount of information. And that requires algorithms and analysis that can be partitioned and operated and processed in parallel with the results rolled up and integrated later. So where can standards help in the big data arena? I want to take a look at some relatively simple models of how to think about big data to see where standards could be useful. So I want to look at horizontally scaled data sources, visit the variety of data sources that we might be looking at, and then look at what is needed to integrate multiple data sources. So this is a simple picture of a horizontally scaled data source. We have some number of computers, n computers, that are distributed and replicated over a single computer room, or multiple computer rooms, or multiple continents, or multiple planets, whatever it takes. So it's horizontally scaled, taking advantage of lots of relatively inexpensive hardware. And we're also scaling the analytics. So this is one solution to the data volume challenge. As we look at a horizontally scaled data source, there are sort of some ease of use type capabilities that we need to look at. We need a language for storing data, a language for querying metadata, a language for querying the data, and a language for specifying the distributed queries. And I believe this is where there's lots of potential for standardization. There also will need to be, for any particular implementation, there'll need to be performance features, a language for specifying how the distribution occurs, how new nodes are deployed and added to the distributed database. These are likely to be product specific, so I don't expect there to be a lot of potential for standardization here. So the place for standardization are the places where there's going to be a lot of interaction with the data. Configuring the database, that should be set up and expanded as needed, but that's going to be a lot of effort up front, and ongoing effort not so much. Maybe adding a new node or every n days or n weeks or so on. But we're going to be querying data, storing data, querying data, doing distributed queries quite often. So that's where we're going to get the most benefit from standardization. So what types of data are we talking about? Well, in the SQL world, we're used to tabular data that where the tables or relations are well designed. The data that's in them is cleansed. We know that it's correct. We don't have a lot of garbage data in there. And it's curated. We know where the data came from. We know what processing has been done on it, and we know how long the data is going to live. There's also spatial data, which either two-dimensional spatial data, maps, three-dimensional maps, and so on, which also is going to be well-designed, cleansed, and curated. Maybe images and videos, which turn out to have well-defined structures, but there's some additional domain information that we need about them. The algorithms that you apply to aerial photos are different than the algorithms that you apply to faces. Photos or videos of faces, and are different from the algorithms that you apply to photos or videos of stars. So we need to have enough domain information to apply the right algorithms to do the analysis of this type of data. We might have documents or very large data sets in XML format, which should have a well-defined document type definition, DTD. There's also a class of data that I've started to refer to as store everything now, figure it out later. And this type of data, representation such as JavaScript object notation, JSON, is often used for this type of data. And it could be things like network packet logs, where we know where the data is coming from, we know approximately what it's going to look like, but it could change over time. This could be data from multiple sensors in an Internet of Things type environment. But the point really is that there are multiple storage models that make sense in particular problem spaces. And so we need to be able to handle those multiple storage models and analyze the storage models to handle the diversity of data that we're really looking at integrating. Another characteristic is the data source ownership. It may be that within a particular company there are data sources that I want to analyze or integrate into my analysis that are owned by the company, and maybe I can go down and find the guy, the person who created the data source, who has the definitions of the data written on a whiteboard in a cubicle, or maybe even documented on paper. There may be data sources that are publicly available. Government data sources from various projects or whatever. There may be data sources that have some restrictions, maybe restrictions on how the data can be used or what parts of the data can be made publicly available. If I create a pretty good data source, then I might want to actually make some money from it. So then I might have a data source that's good enough that people are willing to pay for it, so data for hire. Or maybe there's some sort of derivation of the data that makes it more useful that I can make available. So we need to be able to support the different types of ownerships and the restrictions that come along with those different types of ownerships. So if we go back to my picture a couple slides earlier of a single data source, and we now think in terms of multiple data sources, integrating analysis from multiple data sources, we need a couple of things. We need to be able to find that the data source exists. So we need a data source registry that allows somebody with a data source to say, okay, I have a data source. Here's the type of data that it contains. Here are the restrictions on using it. Here are the contractual requirements for using it. Here are the types of analysis that we can do on this data. And so I can look at a data source registry and say, is this data interesting to me? And possibly even programmatically go off and search for data sources that are of interest and automatically set up the business agreements necessary and identify how to actually access the data source, request some analysis, and get an answer back. So the data source registry needs to have a language or interface for registering data sources. It needs to have the support for discovering the available data sources, the content of the data, the semantics and syntax, the security and privacy restrictions, the provenance, where the data came from, so I can determine if this data is sufficient for whatever my analysis is, and the business agreement information. And I believe that the standards will support the integration of multiple data sources. And so this is an area where standards are going to be of most use as we move forward in this big data environment. So back to the JTC1 Study Group on big data. The study group report identified 16 standards gaps, areas where we believe that additional work should be done in standards development environments to make it easier, better, more productive to take advantage of big data. The report recommended that these standards gaps be assigned to existing JTC1 subcommittees, and that a new working group be created specifically to do definitions and a reference architecture. This slide and the next slide list those standards gaps, and I'm not going to go through them in detail, but these are the topics that the standards committees need to look at to figure out what is needed to fit all of the pieces of the big data picture together. So the recommendation is that these standards gap be assigned to existing JTC1 subcommittees. Telecommunications, programming languages, computer graphics, security techniques, data management and interchange, etc. And I'll come back specifically in a few slides to the data management and interchange SC32 recommendations. Also recommended creating a JTC1 level working group to do the definition of vocabulary in the big data reference architecture, but there's also going to be efforts within the standards groups to coordinate the work across multiple subcommittees. So we're going to have, at the international level, a working group on big data. The US, the ANSI INCITS group, is going to have some sort of group. I also want to mention the NIST Big Data Public Working Group and look at some of the subcommittee efforts. The 2014 JTC1 plenary essentially adopted the study group recommendations in Resolution 28 coming out of the November plenary. This established Working Group 9 on Big Data reporting directly to JTC1 and appointed Wo Chang to serve as the convener. Now, there's a quirk in standards bureaucracy in that for a group to come into existence, it has to have a work item, at least one work item assigned to it. So there are 2 work items that are now out for international ballot that are to be assigned to Working Group 9. And when those work items are approved, Working Group 9 will officially come into existence. Until that happens, JTC1 extended the study group on big data so that the organizations can get moving in parallel with the bureaucracy that needs to happen. Now, the other thing the JTC1 did was to assign the cross-subcommittee coordination to something called the Special Working Group on Management. So Working Group 9 will be responsible for the specifically the vocabulary and the reference architecture. The coordination across subcommittees will be handled by the Special Working Group on Management. The first meeting of WG9 is currently scheduled for April 7th to the 9th in Bremen, Germany. And there are potentially 2 additional meetings in 2015. The new work item proposals, the ballots on those close in March. So by the April meeting, Working Group 9 should be officially in existence. The target for initial standards publication in this area is 2018. The participants in Working Group 9 will be identified by the various national body standards, the standards groups in the various national bodies. Within the US, INCITS will create a mirror committee, a mirror group to the JTC1 Big Data Working Group. I expect this to happen at the end of this month when the INCITS Executive Board meets. The INCITS participants will be registered as participants in Working Group 9. So the INCITS Working Group is the US mechanism for coordinating US standards activity with the international standards activity. The exact structure, the chair, and the meeting calendar for this group are still to be decided. So the INCITS group will provide the US input into the JTC1 Working Group 9. Within the US, there has also been ongoing work by the US National Institute of Standards and Technology in the form of something called the Big Data Public Working Group. The Big Data Public Working Group has been meeting since June 2013 using weekly web conferences. And I've got the website here on the slide to go off and take a look at some of the documents. The output documents, the first draft of the output documents from the Public Working Group were input to the JTC1 Study Group on big data, and I expect that future output documents from the NIST group will be input to the JTC1 Study Group 9 by way of the INCITS big data group. This slide is a list of the public working group output documents. It's worth taking a look at these. They're in version 1 or pre-version 1, and the public working group is currently working on revising and enhancing and maybe actually integrating a couple of the documents. And so in the next couple months there will be new versions of these documents available. But these are all publicly available from a NIST website. Okay, so there are a bunch of tasks that are assigned to existing JTC1 subcommittees. Now I want to look specifically at the recommendations for SC32 because that's where I've spent my international standards time over the last 10 years. So the tasks assigned to SC32 are things such as definition of interfaces to support non-relational data stores, extensions to support the exchange of integration between SQL and non-SQL data stores, metadata and provenance standards, etc. So these tasks are tasks that SC32 needs to review and look at how these tasks or these requirements fit within the current SC32 standards and how SC32 standards can be expanded to support the capabilities discussed here. So there's actually lots of existing work currently in SC32 to support parts of these big data standards gaps. So we need to do additional review. There is some new effort already in progress on some of these, and there's still some things that are going to be completely new work that SC32 will be looking at over the next couple of years. All right, so I've talked a lot about standards, but one of the questions is, why do you care? One of the complications of standards is that the benefits are really long-term. Standards development cycle is 3 to 5 years, and depending on how vendors are participating, the implementations could either be in advance of, but probably not a lot in advance of, in parallel with, or trailing the standards publication. But the ultimate benefit to users of having standards is that it becomes easier to integrate tools. And when you can integrate the same tools across multiple data sources, it becomes easier to find the people, the personnel, who know how to use those tools to take advantage of whatever your data is. It will become easier to integrate multiple data sources so that I can do some analysis on my data and integrate data from an outside data source in a reliable, consistent, repeatable fashion. For the users, better, more complete standards will allow them to focus on the data and on the analysis of the data rather than on the tools to actually do the analysis. From an implementer standpoint, the standards allow them to focus on performance rather than on the interface. So instead of having to go off and define a new language for an interface, you can take advantage of the standard definition and use your development time to focus on performance and some of those underlying capabilities. Having standards in place to make it easier for users to use the tools also ultimately will expand the market for the big data style tools. So I think in the long run there are a lot of benefits for standards. The only thing is that you have to think in terms of 3 to 5 to 8 years to see those benefits. Okay, so standards for big data. To summarize, standards for big data really is a multi-year effort. But a set of suitably crafted standards will aid in the construction of scalable implementations. Now, there's a lot of community experimentation, and the understanding of techniques is evolving fairly rapidly. So the standards process needs to follow what's going on and find those places where it's possible to stabilize interface definitions or interface standards and not inhibit underlying development. Ultimately, standards are essential for integrating multiple data sources. Otherwise, if you don't have standards, you have to go find whoever manages the data source and figure out what the data really is, and so on. And we really want to be able to do that programmatically, relatively automatically. The standards development process needs to use existing standards as foundation because there's a lot of work, particularly in the database area that I'm familiar with. There is a lot of work in the existing standards resolving issues that are common between the current database technology, the SQL database technology, and this new big data distributed database technology. And above all, there's going to be coordination needed between the various JTC1 subcommittees. All right. I really need to acknowledge a number of groups because I haven't come to this understanding of big data on my own. For several years now, I've been part of lots of discussions on the technologies and directions within the JTC1 SE32 working groups, within the NIST Big Data Public Working Group, and then within the JTC1 Study Group on Big Data. And I've also spent a fair amount of time reading articles and books on various aspects of the topic. So I would like to think that my understanding of the problem space has come from that background. Any errors or misunderstandings or misleading statements or completely idiotic comments, I really have to take credit for myself. So if you have questions or comments, feel free to contact me. Email works best in the long term. So thank you for listening to this presentation, and I hope that it is helpful in your understanding of the big data process and the standards efforts that are currently going on.